So we've talked a little bit more about those algebraic numbers and working with them. Let's take a look at some of these formulas we've used. We've had perimeter of a rectangle equals 2L plus 2W. If I give you a rectangle that has a width of 3x squared minus 12 and a length of 4x squared plus 2x plus 7, how would I express the perimeter? Now, usually they might ask you a question like, write an expression for the perimeter of this rectangle or whatever. Same thing. So what we're going to do, our perimeter equals 2, but instead of L, what's the length of this rectangle? 4x squared plus 2x plus 7. Now that is a multi-digit number, so to separate it, we do have to put it in parentheses. So that's just 2L is what I've written there. I just replaced the L. Plus 2W, well, it becomes 2 times perfect, 3x squared minus 12. If you left it like that on a test, I would not mark it wrong. My math lab, however, wants you to simplify it. So to simplify this, the first set of parentheses, there's nothing to do in it, so we got to do something to it to distribute the 2. Very good. 2 times 4x squared is 8x squared. 2 times 2x? 4x. 2 times 7? 14. Now the next set of parentheses, again, there's nothing to do in them, so we do something to them. Times 2. 2 times 3x squared. 6x squared. Now, what am I missing right now? The plus. Very good. 2 times negative 12? Negative 24. Am I done? Okay. We can combine 8x squared and 6x squared makes 14x squared. What should come next? The 4x would be next. There's nothing to combine with it. What's next? 14 and a negative 24 make negative 10. We might have 3x squared by 5x to the third. And I might ask you to express the area. What's our formula for area? Yep, A equals length times width, L times W. So, what am I going to put in there for L? 5x to the third times 3x to the second for W. So as I simplify that or combine that, what do I get?
15x to the fifth.
Perfect. 15x to the fifth. In your notes, I'm going to have you try this one. Express the area. Tell me where to start. I'll give you the formula. A equals L times W. What goes in there? Okay. 3x minus 7 has to go in parentheses. Yes. Then what?
Distribute.
We do distribute the 5x squared times 3x. 15x to the third. 5x squared times negative 7. 5 times negative 7 is negative 35 x squared. Correct? No. Don't do that. I'll catch some of you trying to do that. Don't. Got to stop there. Why do I have to stop here? Yes, x to the third and x squared. And remember, this is not two separate numbers. This is a single number with two digits. This is the x to the third digit. This is the x squared digit. We're missing the x digit and the ones digit aren't there, but it is still just two digits of a number. It's not things that we can combine. That would be just like taking 7,200 and saying, oh, 7 plus 2 is 9. You can't do that, can you? Because this is in the 10 to the third digit. That's the 10 squared. 10 to the 1 and 10 to the 0. You can't combine the 7 and the 2 because they're in different digits of the number. They're different names. Okay. Well, we're going to shift gears a little bit here and come back to actual numbers again. Whole numbers, real numbers from our algebraic numbers. And we're going to start talking about everybody's favorite. Fractions. People moan and groan about fractions. People hate fractions. Because ever since we first saw fractions, we have been taught that there are separate rules for fractions. And that is quite possibly the biggest lie that we tell math students. There are no separate rules for fractions. Fractions are just like any other number. They follow the exact same rules. Now, as we've seen with algebraic numbers, certain types of numbers look different. So even though the same rules apply, they look a little different in how they're used because the numbers look different. So what we're going to focus on today is first understanding the structure of these fractions so that we can then come back and apply the same rules to fractions as we apply to any other number. So the first thing is to look at just a simple fraction like 3/4. Remember, we said the top number, which is called the numerator, is a count. To numerate means to count or to give a value. And the bottom number, which is called the denominator, is a name. So 3/4 means we have 3 of something. Just like having 3 cows or 3 inches. What we have here, though, is fourths. So to start out to define this fraction, the first thing we need to figure out is what is a fourth? Well, the easiest way to illustrate that is to go back to the elementary school illustration. of a pizza or a pie or whatever. Pretend that looks like a circle. If I'm drawing pictures, you're going to have to do a lot of pretending. Just putting that out there. And a fourth means that that pizza is divided into 4 equal pieces. Pretend those look equal. The other way to look at it is it takes 4 pieces to make one whole object. The 3 means that we have 3 of those pieces. So we can either say we have an object that takes 4 pieces and we have 3 of them, or we have 3 pieces, it would take 4 to make a whole object. The first thing we need to look at is renaming this. Back on the first day, we said to add or subtract numbers, you must have the same name. We even looked at something like 2 feet plus 7 inches. And we changed the name of the feet to be 24 inches. So now that they have the same name, then we could add them, right? Well, the same thing here. How do you change the name? Well, from this illustration here, the easiest way we could change the name of this would be to take each of these 4 slices of pizza or 4 pieces and cut them into equal pieces. So I'm going to cut each of them into 4 equal pieces. Once again, you're just going to have to pretend that these are equal. That's actually probably one of my better jobs of cutting that up through the years. But some of my lines weren't terribly straight. But so now, as we look at this, how many pieces does it take to make a whole object? Yeah, 1, 2, 3, 4, counting up to 12, right? It takes 12 whole pieces. How many pieces do we have there in yellow? 9. So we had 3 pieces before. Each of them got cut into 3 pieces. So 3 times 3 gave us 9. It took 4 pieces to make a whole object before. Each of them got cut into 3 pieces. 4 times 3 makes 12. Do we have any more or less pizza than we did before? No, we don't. We have the exact same amount. It just looks different. And when we rename something, that's the key, is we're not changing the amount. We're just changing the way it looks. Just like down here, 2 feet and 24 inches are the exact same amount. They just look different. Here, 3/4 and 9/12 are the exact same amount. They just look different. The reason that they have the same value is this right here. We multiplied by 3 on top and 3 on bottom. Technically, what we multiplied was 3 over 3, or 3/3. Well, what 3/3 is telling us is it takes how many pieces to make a whole object? 3, right? The denominator is 3. So it takes 3 pieces to make a whole object. And we have how many? 3. We have one whole object. 3 over 3 equals 1. A fraction that equals 1. It's called a unity fraction. A unity fraction always equals 1. The numerator has the same value as the denominator. So it's always one whole object. Throughout math, there are several different places where unity fractions come into play. For us, the biggest application they're going to come in is in about week 6 of the summer. We're going to look at measurement conversions. Unity fractions play a huge role in measurement conversions. How did we really change that 2 feet into 24 inches? There was a unity fraction involved there. You get into college algebra or intermediate algebra, and there is unity fractions involved for a lot of different things we do. So we were able to rename this by multiplying the top and bottom by the same number, multiplying by a unity fraction. Now here we just picked the 3. We decided we were going to cut each piece into 3 pieces. Normally we have to figure out what we have to cut it into. Excuse me. So if I have my 3/4, I might be given a specific denominator that I want it to be. Let's say I need this to be 20ths. How do I figure out what the numerator is going to be? Well, first, we have to figure out what did we multiply that denominator by to make it 20? 5. 4 times 5 is 20. So the numerator has to also be multiplied by 5. 3 times 5 is 15. So 15 over 20 has exactly the same value as 3 over 4. If I have 2 over 5 and I want it to become 35ths, what did I multiply that 5 by to turn it into a 35? 7. So what do I have to multiply the 2 by? 7. 2 times 7 is 14. Again, 14 over 35 is exactly the same value as 2 over 5. It just appears different. One for you to try in your notes. Two-thirds into how many twelfths?
8.
Perfect. 8. And to get that, what did we have to multiply the 3 by to make 12? 4. So we have to multiply the 2 by 4 as well. Bless you. We can go the other direction. You know, we said here that the 2/5 and the 14/35 have exactly the same value. I got from 2/5 to the 14/35 by multiplying by 7 over 7. If I want to go back the other direction, I simply reverse that process. 14/35, I can take it back to 2/5 by dividing by 7 on top and bottom. 14 divided by 7 is 2. 35 divided by 7 is 5. So I get back to 2/5. We already established up here that those two numbers those two fractions have the same value. Remember, we had said way back at the beginning of class, multiplication and division are the same operation, just one's going forward and the other, division, is going backward. So anything you can do with multiplication, we can do with division. We can multiply both numerator and denominator of a fraction by the same number. We can divide both numerator and denominator by the same number. Yes?
Okay. Just a question on this. Do you usually, for the numbers, you look at the bottom part first?
If we are trying to change the fraction, like going from 3/4 to something over 20, we have to know what one of them is going to become. Now, all the examples I gave you here, I gave you the new denominator, so then you have to figure out what the new numerator is going to be.
Yeah, so then you look at the bottom.
Yeah, but it depends on what you're given. I could do this. I could give you 3/5 is 12 what? Well, now I'm giving you the numerator first. What do I have to do to 3 to turn it into a 12? Multiply by 4. So what do I have to do to the 5? Multiply it by 4. Now, this is very uncommon that you're going to be given a numerator. Most of the time, as I said, you're going to have a denominator. You have 3/7. You know you want the denominator to be 28. So now, yeah, 7 times what makes 28? 4. So 3 times 4 is 12. So it's 12/28. So most of the time in practical applications, you're going to have to actually figure out what denominator you want. And then once you know that denominator, that helps you decide what you have to multiply by to rename the fraction. But you can, like I did here, you can be given the numerator and have to use that. But it just depends on which one you're given. You have a fraction, and then you're given either the numerator or denominator. So whichever one you're given, that's the one you have to use to figure out what you're multiplying by. So here we went from 2/5 to 14/35. And we decided to reverse it, so we knew we were just going to divide by the 7/7 instead of multiplying by 7/7. Most of the time, however, we didn't, like when we solved an equation, the first one where we built it, we knew how to take it apart. Here we renamed that fraction so we knew how to go back. Most of the time, we don't know what it's been multiplied by. We don't know what we have to divide by. So we have to figure out what to divide by. So we might have something like 12 20ths. And we have to look at that and figure out what can we divide that by to reduce it. And when we're dividing by it, the term is usually reduce. Sometimes it's called simplify. Well, this is where we just talked about those divisibility rules. Now, a lot of you have been told that you have to divide by the greatest common factor. We'll look at that in just a minute here. But for right now, looking at 12 and 20, what is a number that both of those can be divided by? They can both be divided by 4. Very good. 12 divided by 4 is 3. 20 divided by 4? 5. Can I divide both 3 and 5 by anything? Well, they're both prime, right? So there's really nothing we can divide both of them by. Now, you saw the 4 when you looked at that. What if you didn't? What if I looked at this and I said, well, I know they're both even, and all even numbers can be divided by 2. Would it be okay to divide by 2? Yeah, what's 12 divided by 2? 6. What's 20 divided by 2? 10. That's still correct. It's still the same value. It's not finished yet. Because I can still divide both 6 and 10 by the same number. Both of those can be divided by 2. 6 divided by 2 is 3. 10 divided by 2 is 5. Remember, I made a big deal in the first part of the class here of, well, you don't have to worry about dividing by 4 because you can just divide by 2 twice. Well, here, I divided by 2 twice. I ended up in the same spot. Well, it's so many high school teachers and elementary school teachers say you have to find the largest number that goes into both. No, you don't. It's just it takes more steps if you don't. Just like if you do 48 over 60. Some of you might look at that and see that both of those can be divided by 12. But if you don't sit there and struggle with it. I would look at these and say, well, can both of them be divided by 10? Well, the 60 can, but the 40 can't. Right? Can both of them be divided by 5? No. How about 2? Yeah, they're both even. So let's divide by 2. Now, I know you said 6. And yes, you could divide by 6, but 24. 48 divided by 2 is 24. 60 divided by 2? 30. Now, a lot of times, even just dividing by 2, once that fraction's a little bit small, the fraction has the same value, but once the pieces of the fraction are a little bit smaller, it becomes a lot easier to see what they can both be divided by. Here, I can see they can both be divided by 2, again, or I see they both can be divided by 3, but they're still both able to be divided by 6. What's 24 divided by 6? 4. How about 30 divided by 6? 5. 4/5. And that's it. There's nothing that can divide into both 4 and 5. We're done. I could have divided by 2 again and then 3. It doesn't matter. I would still get to that same spot. You do not have to find that largest common factor. Now, if you're really insistent on finding that greatest common factor, there is a way to do it. We talked about doing those factor trees. We did 48. What's one number that goes into 48? Let's do 6. 48 divided by 6 would leave us with 8. Are either of those prime? Nope. 6 can be split up into 2 times 3 or 3 times 2, either way. Both of those are prime. 8 can be split up into 4 times 2 or 2 times 4. The 2 is prime. 4 splits up into 2 times 2. So 48 is 2 times 2 times 2 times 2 times 3. 60 is 2 times 2 times 3 times 5. If I did the same thing with 60, that's what I'd end up with. I'm just saving some time by giving that to you. Greatest common factor. The key word, the key part of that is common factor. What factors are in common? Well, there's a 2 in common. There's another 2 in common. This one has more 2's, but the other one doesn't. But they do have a 3 in common. So my common factors are a 2, another 2, and a 3. 2 times 2 is 4 times 3 is 12. What number divides into both 48 and 60? 12. 48 divided by 12 is 4. 60 divided by 12 is 5. Now that's a lot of work to find that number, but if you absolutely insist on finding the largest one right away and doing it in one step, that's one way to find that greatest common factor. We're going to use that factoring, by the way, for other processes. When we start looking for least common multiples, and least common multiples are actually the same as least common denominators, we're going to end up with that same thing going on. What we've been looking at so far are what are called proper fractions. In a proper fraction, it represents less than one whole object. So in other words, however many pieces it takes to make one whole object, we have less than that amount. In other words, the numerator has been smaller than the denominator. An improper fraction is one where the numerator is larger than the denominator. Like this, 5/4. Well, don't get ahead of me here. 5/4 is more than one whole object. Because it's saying it takes 4 pieces to make a whole object. We have 5 pieces. That's more than enough pieces to make a whole object. Now the word improper is kind of deceiving. Improper implies wrong. It is not wrong. It's just not a preferred way of writing it. There are times, however, where writing it like that is preferred. In fact, there's times like that where we need to write it like that so we can work with it. And as we go through the next couple of days dealing with fractions, we'll look at some of those times. So if I have an improper fraction like 44/7, obviously the numerator is bigger than the denominator. This is saying it takes 7 pieces to make a whole object. We have 44 pieces. So not only do we have enough pieces to make a whole object, we have enough pieces to make several whole objects. So the first question we have to ask is how many whole objects can we make? The way we answer that question, 44 divided by 7. If you punch that in your calculator, it comes out to be something like 6.28571429, approximately. What does that mean? You get 6 whole objects. Yes. Now the second question we have to ask, how many pieces are left over? And now in our first homework assignment, we had those division and remainder problems. And we struggled a little bit with them because what appears in the decimal here tells us almost nothing about the remainder. Remember, the way we would do that, we would take 6 divided by 7. 6 divided by 7. Let me try that again. 44 divided by 7. Took the numerator divided by 9. 44 divided by 7 does give us the 6.285714286. The 6 was our whole objects. The 6 was our whole number. If we subtract the 6 and we multiply back by the 7, that tells us there's a remainder of 2 here. So that was 2/7 left over. So all this is a division and remainder. The result of the division is the whole objects. The remainder is how many pieces are left over. So if I were to take 44 divided by 7, well, 7 goes into 44 6 times. 6 times 7 is 42, which means there's 2 pieces left over. So that is 6 2/7. So if I have 25/6, what I am going to do is do 25 divided by 6. How many times does 6 go into 25? 4 times. What's 4 times 6? 24. How much is left over? 1. So this is 4 whole objects with 1 piece, or 1/6, left over. (17/3). I'll take 17 divided by 3. 3 goes into 17 how many times? 3 times 6 would be 18. So we got to drop down to 5. 5 times 3 is 15. So there's a remainder of 2. So yes, that is 5 2/3. In your notes, I want you to do 19/4 and 25/3. So for the first one, 19/4, what am I going to divide? 19 divided by 4. Good. 4 goes into 19 how many times? 4. 4 times 4 is 16. How much is left over? So 19/4 is
4 3/4.
4 3/4. Yeah. For 25/3, what am I going to divide? 25 divided by 3. 3 goes into 25. 8. 8 times 3. 24. How much is left over?
1.
1. So 25/3 is 8 1/3. Very good. So that's simple enough, right? Well, just like when we renamed our fraction and then reduced the fractions, we went backwards. Same thing here. There will be times where we want to go the other direction, where we want to go from the mixed number back into the improper fraction. So if I have 2 3/8, and I want to make that back into an improper fraction, first thing I have to do is break the whole object into pieces. Well, I have my whole object is 2, right? How many pieces does each whole object get broken into here? 8. Yeah, the denominator tells us it takes 8 pieces in each whole object. So what do I do to my 2? Multiply by 8. Good. There are 16 pieces in that whole object. Then I take that and combine with the other pieces. Because there are pieces already there, that would be the 3, yes. So 3 plus 8 is, or not 3 plus 8, 3 plus 16 is 19. Those are all still 8s. Perfect. Now in practice, I'm probably not going to write it out quite that specifically. I'm just going to take my whole object of 5. What am I going to multiply it by? 4. 5 times 4 is 20. So I add the 20 to the 3 to get 23/4. Or if I have 7 1/3, what do? 7 times 3 is 21. 1 plus 21 is 22/3. In your notes, four 2/5, I want you to convert that back into an improper fraction. And 3 5/6. Convert that into an improper fraction. So 4 2/5. Tell me what to do first. 4 times 5 is 20. 2 plus 20 is 22/5. Good. 3 5/6. What do I do first? 3 times 6 is 5. 5 plus 18 is 23/6. Wonderful. Now we are going to experience some numbers that are way uglier than this. Obviously, I've been keeping them nice and neat for us, but the process will still be the same. You know, I might have 13 4/7. To turn that into an improper fraction, what am I going to multiply? 13 times 7. I may have to write it out to make it work. 3 times 7 is 21, so 1 carry the 2. 7 times 1 is 7, plus 2 is 9. 91. So that's 91 added to the 4, which is 95. Very good. It says 95/7. Same process, it was just bigger, uglier numbers. I might have 138 elevenths, and I want to convert that into a mixed number. What am I going to do? 138 divided by 11. Does 11 go into 1? Nope, so we'll leave that blank. How about 13? 1. So we put a 1 above the 13. 1 times 11 is 11. 13 minus 11 is 2. Then what? Bring down the 8. 11 goes into 28. Twice. 2 times 11? 22. There's 6 left over. Anything to bring down? No, we are done. So that is 12, and there are 6 elevenths left over. So it's uglier numbers, it's still the same process. And if you need to, obviously you can use your calculator to step yourself through this. You can do 138 divided by 11. Now it's going to say 12.5454. That's where the 12 comes from. Write in the 12. And then come back and do, okay, 12 times 11 is the 132. You'd put, let me write this all out. So I divided and I got the 12. 12 times 11 is 132. And then I subtract to get the 6. So then it's 12 and 6 elevenths. So your calculator can shorten that up a little bit rather than doing it all out by hand. But I still write this out just so I keep track of where the pieces are. Now, most of you that have fraction calculators, how many of you have a fraction calculator with you today? That one should do it, yes. This is where if you're using a cell phone calculator, I have seen a couple of downloadable calculators for the cell phones that do fractions, but the TI-30 calculator does fractions way easier, way simpler. You have a button on your calculator that says ABC. That is your fraction key. What I'm going to have you enter is type in the 13811. So type in 138, you press that ABC key, and then type in 11, and press equals, and what does it do?
12 and 6.
Yeah, that stands for 12 and 6 elevenths. That little like miniature U thing is actually just the space.
Okay.
It separates the whole number from the fraction. Some of you, if you have an older version of the calculator, it might appear like this. That symbol there is just the slash. It's just that particular model calculator doesn't have the slash ability to display it. So yeah, these fraction calculators, as we go through, I will show you some of the ways to make them work. They do wonderful things. By the way, if you wanted to go from a mixed number into an improper fraction, it's a little bit trickier, and it depends on which model you have. You use that to enter a mixed number, first of all. Let's say you have 7 1/3. To enter that in the calculator, you do 7, you press the ABC key, then you put in the numerator, press the ABC key, and then you enter the denominator, third. You hit equal, and it will display 7 1/3. To change that into an improper fraction, you're going to have to look a little bit. For some of you, it'll be just above the ABC key. Some of you, it's above what's called an SD key. The key might look like this, SD. Above that key, it's going to be a second function on all your calculators. You'll have ABC to DC. It looks like that. So what you would do is, once you've entered the 7 1/3, you hit the second or the shift key, and then press that key, and then hit equals. You may have to hit equals twice, depending on your calculator. 22 thirds, yes. 7 1/3 is 22 thirds. Did you get it to work, Robin?
No, I don't see that. I got FD.
Okay.
I don't see SD in there anywhere.
Let's see on yours. It's going to be just above the ABC.
Oh, right there?
Yep, so you do second,
Yep.
then hit ABC.
Okay.
Is that purple one?
Oh, cool.
Thank you.
You bet. So these calculators do some wonderful things. Okay. If I give you a fraction of 0/8, what is its value? 0. Because what that's saying is it takes 8 pieces to make a whole object, and we have none. If I give you a fraction of 8/0, what does that mean? It means nothing. It doesn't mean 0. It's meaningless. It is undefined. The reason is, this is telling me it takes 0 pieces to make a whole object. In other words, those pieces don't exist. If it takes 0 pieces to make a whole object, how can I have 8 pieces? How many whole objects does 8 pieces make? Well, it doesn't take any of them to make a whole object. Remember, we said that there is a link between a fraction and division. If we have 3/4, we can do 3 divided by 4 is going to give us 0.75. That's the decimal equivalent. A fraction can be thought of as a division problem. I can do 0 divided by 8. Your calculator will spit out 0 just fine. If I do 8 divided by 0, it is going to give you an error. We can never have a denominator of 0. We can have a numerator of 0, but never have a denominator of 0. I'm going to foreshadow a little bit. Not necessarily this course, we don't get into it a whole lot, but in other courses we might. 3/x as a fraction, we have to specify that x cannot equal 0. Because if x were 0, that would be 3/0. That would be a very bad thing. Actually, I'm going to make this even simpler on us. 5/x minus 4. Are there any values that x cannot be? Well, if x were 0, what's 0 minus 4?
-4.
-4. Is 5/-4 okay? Yeah, it's a negative 1.25. What can x not be? X can't be 4. Because 4 minus 4 would be 0. Yeah. So there are some things that we got to be careful of that x cannot be. Okay, our last topic for today, and then I'll let you guys go for your weekend. And we're just going to talk about it briefly. Since we had our pieces of the pie here for fractions, kind of links into circle graphs. Circle graphs are usually based on percents. Like, let's look at online, face-to-face, and ITV for classes. So different ways of taking a course. Let's say our number of students. Let's say for a particular course, let's look at math with business applications or business math for fall. Let's say that there are 30 students taking that class online. There are 50 students taking it face-to-face and 20 taking it ITV. If I want to make a circle graph, first thing I have to do is I have to figure out the percent for each of them. To figure out the percent, I first find a total. If I add up 30, 50, and 20, I get 100. To find a percent, I divide each number by the total. Well, in this case, it'd be 100, so that's going to be 0.30. 0.30 is 30%. We'll talk more about percents over the next couple of days. 50 divided by 100 is going to be 0.50 or 50%. 20 divided by 100, 0.20 or 20%. Well, these are pretty simple because I made the total come out to 100. Percent means out of 100. So when you divide by 100, that is your percent. Now, if this were 30 years ago, well, maybe even more than 30 years ago now, to make a circle graph, we would then say, well, a full circle, we said, was how many degrees? 360 degrees. We would find 30% of 360. Then we'd take our protractor out and we'd measure that angle, figure out what angle that has to be with the center of the circle and all that. Well, we don't have to do that anymore because almost every computer comes equipped with some sort of a program, usually a spreadsheet program, where you can just plug in the numbers and you can make that, if you want that perfect circle graph, it is right there in seconds. For example, using Microsoft Excel. Highlight it, go to Insert. They use pie graph instead of circle graph, but there it is. And I can do all sorts of things to reformat it. I can actually put the names in the chart or whatever. I can put the numbers there. I mean, it's that quick. So we don't need to be perfect with ours. But I do want us to be able to estimate. If I were looking at this, what is a half a circle? What percent is half a circle? You're thinking degrees, yeah. It's not 50% is the percent is. Quarter of a circle? 25%. If I did half of a quarter or 1/8, 12.5%. Half of 25, right? I can use those to come out with pretty rough. Actually, there's one that's exactly 50%. So that's going to be the face-to-face. The online is 30%, which is slightly more than 25. So I'd go slightly more than 25. That's online. This remainder here is ITV. So that's a relatively accurate circle graph without having to go through a whole lot of effort. Now, these added up to 100, so that made it a little simpler. If they don't add up to 100, let's say we're going to survey people on their favorite color. We're only going to give them 3 choices, red, blue, and green. And let's say the number that choose red, let's say there is 13 that choose red, 11 that choose blue, and 16 that choose green. We need to find the total. What's the total here? 40. So to find percents, I'm going to divide each of them by 40. What's 13 divided by 40? Or 0.325. Perfect. That is 32.5%. Decimal goes over 2 spots. We'll explain why you had to move the decimal over the next few days, by the way. 11 divided by 40. Careful, something's a little off there. 11 divided by 40, you got some. You did 40 divided by 11.
Oh.
11 divided by 40 should be 0.275. So 27.5%. Yep. 16 divided by 40. 0.4, right? So what percent is that? 40%. So again, on our circle, well, 40% is somewhat less than half. There's my green. 27.5 is slightly greater than a quarter. So that'd be my blue. The rest of it must be red. Close enough, right? Okay. The other application of this is, let's say we have a chart that looks like this. Let's say this is 31% preferred choice A, 26% preferred choice B, 43% preferred choice C. Let's say out of 210 students, how many prefer choice B? What that's asking us to do is just find 26% of 210. Now, we haven't done percents yet. So the shortcut here, the quick and dirty way, is just going to be 210 times 0.26. So like I said, over the next week, we'll look at percents a little more closely. Actually, it might even be after next week, but we will look at percents a little more closely yet. And we'll explain why the calculation goes the way it does. For now, I just wanted you to have that so that when you see some circle graphs in the homework, you don't get lost. Okay, that is it for new material. So I'll let you guys have the last 10 minutes to start on homework if you want to. There is a new quiz. That quiz is due at 11:59 p.m. tonight. Then there's a new homework. That will be due on Monday. Now remember, you have those test corrections to do. My limit on test corrections is generally the next test. Our next test is next week, Thursday, 1 week from today. So it's something to work on over the weekend. So if you come in on Monday, I will take some time at the beginning of class to answer questions on that test if you're struggling to figure anything out. Make sure you guys remind me if you have, I may not remember to ask, but if you have questions on that test, speak up at the beginning of class on Monday and make sure I go through them for you. So that's the problem with summer, is it feels like we just took a test. Well,
You said we're cramming
Yeah.
the whole semester into 8 weeks. So.
technically, the next Thursday is the end of week 6.
Is it really?
Yeah. Today is the end of week 4, technically. Okay, like I said, the computer labs are there. If you want to work on homework or quizzes, go ahead.